Hey AP, in this video we're going to talk about heat and calorimetry. So this is the beginning of our new unit on thermodynamics, and thermodynamics is the study of heat exchange in chemical systems. So we need to talk about heat versus temperature, heat transfer, and then how can we measure that and then find out information about a chemical reaction that we're looking at. So first, heat is a transfer of energy. It's not a substance. We might say something's hot, but that's our interpretation of the energy involved. We know that heat transfers from hot to cold. So that means if you have an ice cube inside your hand, the heat from your hand is going to the cold ice cube, going from hot to cold, and that's what's melting our ice cube. And this happens until both become at equilibrium or they get to be the same temperature. Heat is different than temperature. Temperature, we know, is a measure of the average kinetic energy of molecules. So that we looked at when we looked at how fast molecules are moving. The faster they were moving, the more energy had. We said they were at a higher temperature. And this is relative to the Kelvin temperature. Okay. So as Kelvin temperature increases, so does the kinetic energy, and it increases proportionally. So if we double our temperature in Kelvin, we also double the kinetic energy. And this has to do with the fact that kinetic energy is equal to 1/2 mv squared, where m is our mass, and v is the velocity. So the kinetic energy has to do with the mass of a molecule along with how fast it is going, its velocity, which is speed with direction, and that makes up its kinetic energy. So we've talked about how light things can have the same kinetic energy as a heavy thing, but the light things are moving faster, and that has to do with the speed, not necessarily the kinetic energy. We've also talked about how gas molecules in particular at high temperatures are moving really fast, and so we show that with long arrows. They're not moving the same speed, but they have an average kinetic energy that is much higher than those at the low temperature. We show that by having the short arrows. These are moving much slower or with less kinetic energy. We can also represent that with our Maxwell-Boltzmann distribution, where we have our number of particles on the y-axis, our energy of the particles on the x-axis. If I have particles that are at a low temperature, they are going to have an average energy that's pretty low. Okay, so I'm going to draw this down, and then it kind of curves off here because some are at higher energy, but most of which are down here at the low energy. But if I heat up those particles, I'm increasing their kinetic energy, and that is going to mean on average, my particles have a higher energy. And we can't draw that up here because that would mean the area under my curve would be bigger than I would have here. So remember, that's a little shorter at high temperatures. Then we curve off here. So you can see that now here I have more particles. Let's say, this is either an activation energy or the energy that we need to make our reaction happen. We can see that our cold molecules, we only have this many available to us to have the reaction happen. They're much colder. Whereas my hot particles, I have all of these that are at enough energy. Now, there are still some that are at low energies, right? There's still some particles that are not going to react even though they're at a higher temperature. But on average, there's many, many more at a higher energy. So we say this is high temperatures. And my blue was at low temperatures. All right. So again, heat transfer, we could transfer energy from these high temperature molecules to the low ones, and then we'd have some sort of middle ground here, right? We could do that, but it's a transfer of energy from hot to cold until the system is at equilibrium, and we call this thermal equilibrium, and this equilibrium is where we have equal temperatures or equal kinetic energy of molecules. So we can study that and quantify that using something called calorimetry. And calorimetry is something that we have looked at last year in chemistry. It was in our one of the very first units that we did. So calorimetry is an experimental technique used to measure heat changes in a chemical system. Okay. We'll talk about the difference between system and surroundings in a minute. But the chemical reaction is put into thermal contact with a heat bath, usually water, and then we measure the change in water. So here is an example of a calorimeter. I'm going to zoom in so you can see that a little better. So our very fancy calorimeters are actually styrofoam cups. And so we have the styrofoam cup, and inside of it, we've put water in, and then we use a thermometer. We poke a hole through the top if it has a cover, and we'll measure the change in temperature of the water. So we'll know our initial temperature of the water, the final temperature of the water. Usually, either you're doing a reaction in water, or you would place inside of here some sort of reaction vessel, which is like a cup. And you would do the reaction in the cup, and it'd be a metal cup. And so then the reaction would heat up or cool down. We could also heat up a hot piece of metal, set it in the cup, and then we would know how hot the metal started, how it ended. But we could measure the change in temperature using the water. So this is a calorimeter, and we'll use something like this in the labs that we'll do in class coming up. Zoom back out. So we remember that one of the ways that we can quantify this is to use our equation where Q equals MC delta T, where Q is my variable for energy, which we calculate in joules or J. M is my mass in grams. Delta T is the change in temperature. Remember that is T final minus T initial. So delta just means change in. And C is specific heat. And specific heat is the energy required to raise 1 gram of a substance 1 degree Celsius. So this is experimentally determined, and then we have tables of these values. So you'll be given a table of values if you're asked to find something out based on its specific heat. Otherwise, they're usually given to you. Okay. So up until this point, we have looked at this equation, and we've said, well, the heat energy given off by the hot metal is absorbed into the water. So the metal cools, the water heats up. That's what we care about. But now that we're in AP, we also have to think about the fact that, well, this styrofoam cup is going to also absorb some of the heat. So the cup also absorbs heat. And we need to start factoring that in because that's going to impact how much energy is actually transferred. So our numbers are going to be off a little bit up until this point, but now we can start factoring in the heat absorbed by the water, and the heat absorbed by the calorimeter is equal to the heat given off by our hot metal. So again, information about the water, still the same, MC delta T. But the mass of the calorimeter doesn't matter. It just matters the change in temperature that it experiences, which is the same change in temperature that the water would experience because it's at equilibrium together. They start at the same temperature, they end at the same temperature. And then we'd have to be given the specific heat of our calorimeter. Important to note that the specific heat of our calorimeter is given in joules per degree Celsius. And that makes sense because we don't want to have grams in here because we don't care about the mass of our calorimeter. So this is another factor that we'll have to add in when the information is given to us. Sometimes it's not, but most of the time we're told information about our calorimeter, so we need to factor that in. We can talk about our calorimeter as a system and surroundings. So the system, the thing that's changing, is our chemical reaction. And then we look at how heat changes from our system to our surroundings. So heat goes from the system to the surroundings, and our surroundings would be what's surrounding our metal, which would be our water bath. So because what we're measuring is the water bath, if my water bath increases in temperature, that means that my actual reaction is decreasing in temperature, right? Because this is increasing, it's gaining energy and temperature from my reaction. So if my water bath increases in temperature, that means that my reaction is exothermic. Okay, my reaction is giving off heat energy to my surroundings. But if the water bath, that should say decreases. That doesn't make sense otherwise. If my water bath temperature decreases, that means my heat energy is going from the water into my metal. And that means, or my reaction that's happening in here. So that means that my reaction is endothermic because my reaction is absorbing the heat energy from my surrounding water. Okay, so we'll explore this more with a lab coming up here in class. I think we'll do Hess's Law Lab, but we'll do some labs that we get to use the calorimeter so you can kind of see what that looks like. So with this, we can do lots of different calculations. So we're going to go through a couple examples here. Other thing on your reference guides, we are down here in the thermochemistry part. So second page, backside, you have your Q equals MC delta T. Okay. Eventually we'll get into this equation too, the delta H. Notice that this does not show that the total heat energy is water plus the calorimeter, so just be aware of that. And then we also are not given our constants for specific heats. So let's go ahead and write those in because we'll use them for class. They won't come up on the AP exam, but you'll want to have them to reference. So a couple of values, specific heat of water. So specific heat of water is 4.18 joules per gram degrees Celsius. So that's one that we'll use quite a bit coming up here in our practice problems. So you can go ahead and add that on there. Just put a little W for water, H2O, just so you know what that is. And that's liquid water, not heat, steam or ice. All right, so example 1, we have a piece of unknown metal. The mass of 5 grams is heated to 98 degrees Celsius, dropped into 15 milliliters of water at 22 degrees Celsius. Final temperature of the system is 27 degrees Celsius. Find specific heat capacity of the metal. So we've got two things going on. We've got a hot metal is placed into much cooler water. So we have a calorimeter in action. Right? We have placed our hot metal into cool water, and we've measured the change in temperature of our water. So something to help us with these is to set up a short little chart where we have information about our metal. Let me get so my hand's not in the way. So we have information about our metal, and we have information about the water. We know that if we're looking at specific heat capacity, the formula that has specific heat capacity, temperature, mass in it is our Q equals MC delta T. So I'm going to want Q, M, C, and delta T is T final and T initial. This is all information that's going to be helpful. We know that the metal, which is hot, is going to decrease in temperature and heat, and the water is going to heat up. We can see that the water goes up in temperature, which means that the metal must go down. And we know that the Q, the amount of heat given off by the metal, so directionality, we put the negative sign, is equal to the amount of heat gained by the water. Okay, but they're opposite in sign. So same magnitude or value, but one is negative, one is positive. So from our calculation, or from our question, it tells us we have 5 grams of metal, so 5.00 grams, heated to 98 degrees Celsius, so that's its initial temperature. We need delta T down here. Dropped into 15 milliliters of water. Remember that 1 mil of water weighs 1 gram of water. So that means we have 15 grams of water. Water originally at 22 degrees Celsius. Final temperature of the system is 27 degrees Celsius. So that is both the water. If Remember, it comes to thermal equilibrium. So it's the water and the metal. Then it asks us to calculate specific heat capacity of the metal. So this is what we're trying to find. And we know that water has a specific heat of 4.18 joules per gram degree Celsius. Delta T, we can figure out by taking our T final minus T initial. So T final, 27 minus 22 gives me 5. And then we go to 2 decimal places. 5 degrees Celsius. And then second one, 27 minus 98 is negative 71, common to the tenths place, so negative 71.0 degrees Celsius. So we know all our information. So now we can go ahead and plug in. So remember this, Q is equal to negative M of my metal, C of my metal, delta T of my metal, which is equal to M of my water, specific heat of my water, delta T in water, right? I've just plugged in for Q because we said Q is MC delta T. So I'm going to plug in my values. So negative metal, 5 grams. Specific heat is what we're looking for. Change in temperature, negative 71 degrees Celsius equals mass of water, 15 grams. Specific heat of water, 4.18 joules per gram degree Celsius. Change in temperature, 5 degrees Celsius. So multiply these together. 15, 4.18, 5 gives me 313.5. Grams cancel out with grams. Celsius with Celsius, so we're left with joules. And then on this side, negative 5 times negative 71. I get 355. So 355. And we've got, let's see, grams degrees Celsius, because those two units get multiplied together. That's times our specific heat of our metal. I want specific heat, so I'm going to divide off 355 gram degrees Celsius. 355 grams degrees Celsius. So I get the specific heat of my metal, 313.5, 355. I get it to be 0.883. Let's look back for sig figs. 3 sig figs. 3, 3, 4, 4. So I have 3. My units, which is pull off of here, joules over grams degrees Celsius. Joules, grams degrees Celsius. And there we go. So my specific heat of my metal, 0.883 joules per gram degree Celsius. Okay. In my next example, I have the burning of 1.10 grams of glucose in a bomb calorimeter. I think this should say changes. Oh, causes the water temperature of the bomb to rise from 24.9 to 28.9. Calorimeter contains 975 grams of water. Heat capacity of the calorimeter, we've got to factor that in now, is 763. Calculate heat of combustion of glucose expressed in kilojoules per mole. All right. Well, we know that the total amount of heat of combustion of the glucose is equal to the amount of heat the water gained plus the amount of heat that the calorimeter absorbed. Okay. I know about my water mass, specific heat, delta T of my water. And remember, Q of the calorimeter is delta T of the calorimeter times specific heat of the calorimeter. So plugging in, I have 975 grams of water. Specific heat of water, 4.18 joules per gram degree Celsius. Change in temperature, the water went from final minus initial, so 28.9 minus 24.9. Plus, now that's the change in temperature of the water, which is the same change in temperature as our calorimeter. So change in the calorimeter, same thing, 28.9 minus 24.9, which I think is 4 degrees Celsius. And then my specific heat, my calorimeter is 763 joules degrees Celsius. So plugging that in, so you can see 975, and then 28.9 minus 24.9, which is 4, plus 28.9 minus 24.9 times 763. And I get this large number, 19354. And this is, let's see, units wise, this is degrees Celsius. That cancels out with that. Grams with grams, I'm left with joules here. Degrees Celsius, cancel out with this degree Celsius, so joules. So this is joules. All right. It asks us to figure out heat of combustion expressed in kilojoules per mole. So remember, there is 1,000 joules in a kilojoule. So dividing this by 1,000, I get 19.354 kilojoules. And I've combusted 110 grams of glucose. So I need to convert grams to moles to see, well, how many moles made this many kilojoules. So 1.10 grams of glucose, C6, H12O6. And my molar mass of glucose, which I calculated before, is 180.18 grams per 1 mole, which means when I do the math, 0.00611 moles of glucose. All right, so that means that this is how many moles I've burned. This is how many kilojoules of energy that I have released. So to figure out my heat of combustion in kilojoules per mole, I'm going to take my 19.354 kilojoules divided by my moles. And when I do that, 0.354, I get 3,167.6. 3,167.6 kilojoules per mole. I got around to sig figs. So going back up to my question, 3 sig figs, 4, 3, 4. This is a constant, so it doesn't impact us. So all our measured values, smallest is 3. So 1, 2, 3. We round up. So 3,170 kilojoules per mole. All right, so that's another type where we factor in our calorimeter, absorption of energy, and the water. Let's look at a third type of question that we could see. So in example 3, it says ethanol can be burned in a bomb calorimeter. And 5 grams of ethanol is burned in a calorimeter whose heat capacity is 43.8 kilojoules per degree Celsius. Temperature increases by 6.5 degrees Celsius. Write a thermochemical equation for the combustion of ethanol. So if it's combusting, that means that I'm probably not doing it in water because that would put it out. So all of the energy looks to be absorbed by the calorimeter. So that means that the total energy given off by my ethanol is equal to the energy absorbed by my calorimeter. And we know that it's given off because it's burning, right? It's an exothermic reaction. We know that the heat of a calorimeter is equal to the change in temperature times the specific heat of the calorimeter. We're told the change in temperature is 6.5 degrees Celsius. And our specific heat of the calorimeter is 43.8 kilojoules per degree Celsius. So 6.5 times 43.8 is 284.7. 284.7 kilojoules, because my degree Celsius cancels out. All right, so that's kilojoules. But if I want a thermochemical equation, I'm going to want that answer in kilojoules per mole, because then it doesn't matter how many of anything I have. Once I know my moles, I can calculate it. So that means that my 5 grams, I need to convert to moles. So 5 grams of ethanol, C2H5OH. My molar mass of ethanol is 46.08 grams per 1 mole, which means I have 0.1085 moles of ethanol. So just like we did up here to get a molar heat of combustion, we'll get a molar heat here as well. So my 284.7 kilojoules divided by my moles, 0.1085 moles. 0.1085. I get 2,623.96. 2,623.96 kilojoules per mole. I care about sig figs. Going back to my measured values, 5, that's 5.0 grams. 3 sig figs, and 2, so I'm going to round to 2. This makes it 26,000 kilojoules per mole. Okay, so that's the amount of heat released when ethanol is burned. So ethanol is burned. Our chemical reaction is C2H5OH. It's burned. So we've got oxygen. Combustion reaction. So we're always going to make carbon dioxide and water. And we are releasing 2,600 kilojoules per mole of heat energy. So to balance this, I need a 2 here. I need 5 and 1 is 6. That's 3 there. 4, 5, 6, 7 minus 1 is 6. So 3. You might also see this written C2H5OH plus 3O2, 2CO2, 3H2O. And then you'd see something where you'd see delta H, which we haven't talked about yet, but we'll talk about soon, is a molar enthalpy, so the heat given off. You'd see that as negative 2,600 kilojoules per mole, because that's heat given off. So you might see it like this. I'm going to ask for a thermochemical equation. We want to show heat energy in our reaction like that. So those are 3 different types of questions that we can see in terms of calorimetry and looking at the heat exchange from a chemical reaction.